Okay, we should get started. So just another reminder, there will be an exam in here a week from today, and so try to get those practice exams mounted here soon. So where we're headed now today is we're going to pick up the concepts we finished with last time, where we described how the erythrocytes were peculiar cells. In fact, we described them as formed elements, not having all of the characteristics of a normal cell. And we ended with the idea that there was a kind of lineage for all of these erythrocytes, that they started out as hematopoietic stem cells and then matured into proerythrocytes, became normoblasts to reticulocytes. Reticulocytes then left the red bone marrow, went out into the blood vascular compartment, and in the blood vascular compartment, those reticulocytes, in a matter of a day or two, would then mature into proper erythrocytes. And so typically, in blood, we have about 0.5 to 1% of all of the blood cells being these reticulocytes. So only a small fraction, but in fact, that gives you some hint that the fact that we are turning over these erythrocytes throughout our lives. And that's one of the ideas we'll come up with here today, and we'll begin discussing the hormonal control of erythrocyte production. And of all places, we're going to find that there's a hormone called erythropoietin that comes from the kidney. But the kidney turns out to be an excellent place to monitor for blood oxygen levels, because the kidney receives a tremendous amount of blood from each circuit. So every time your left ventricle beats and sends blood out into the systemic vasculature, something like 20 to 25% of that blood is dedicated to being carried through the kidneys. And so there's a tremendous blood supply to the kidneys, and it turns out that it's cells in the kidneys now that are going to be monitoring for oxygen levels. And when oxygen levels begin to drop, that's an indication that the erythrocyte numbers are inadequate. So you're simply not oxygenating blood adequately, and you don't have enough erythrocytes. And so that gears up a series of cells, in fact fibroblasts, in the kidney to generate this protein called erythropoietin. This is a glycoprotein hormone. So immediately when you see this idea it's a glycoprotein hormone, there must be transmembrane protein receptors for this glycoprotein hormone. And sure enough, when we begin to look at where we find most of these glycoprotein hormone receptors, they're found on the precursor cells of the hematopoietic stem cells. They're found on the precursor cells of the erythrocytes, predominantly on the proerythrocytes and perhaps even some of the precursor cells to the proerythrocytes. And then this glycoprotein hormone acts as a kind of growth factor. It acts as a kind of signal to keep these cells alive so that it increases the overall production of erythrocytes. And we do this all the time. And we'll talk a little bit about how if we're under low oxygen stress, what we'll do is we'll upregulate the amount of this glycoprotein and increase the number of erythrocytes produced. That will then bring us to a short discussion on the structure of erythrocytes. And when you hear the structure of an erythrocyte described, it's said to be a biconcave disc. Now, what this means is that it's a very thin cell. It's no more than about a micrometer or two thick at its thinnest point. And the reason for this very thin structure is that its function is to carry oxygen. Its function is to be a bag of hemoglobin, which is the oxygen-carrying molecule. And so we reduce the diffusion distances that are necessary for the oxygen to move from the alveolar space, that we'll talk about a little bit later in respiration, into the erythrocyte. So we have these very short diffusion paths so that we can charge up the hemoglobin with oxygen in a matter of a fraction of a second as those erythrocytes are passing through the pulmonary capillary beds. Then we'll drill down and look at the main component of erythrocytes. The main component of erythrocytes is the protein hemoglobin. And hemoglobin is an iron-containing molecule. And the iron is contained in something called a porphyrin ring. And if you take a biochemistry class, you got really down into the details of this. You'll find a whole lot about how these porphyrin rings are synthesized. Turns out, oddly enough, they're synthesized in mitochondria, then shipped out into the cell cytoplasm, where they're incorporated into the protein parts of the hemoglobin. And we'll find that every hemoglobin molecule is constructed from 4 protein chains. There are 2 alpha chains and there are 2 beta chains. And these alpha and beta chains. Each one of these chains contains an iron atom incorporated into a porphyrin ring. And because of the electron sharing between the nitrogens in the porphyrin ring and the iron atom itself, we generate this iron atom with a particular redox state which allows it to bind to oxygen. It can bind to oxygen and then carry oxygen throughout the body. And the wonder of this particular molecule is that not only does it bind oxygen, but it binds oxygen relatively loosely, so that in regions of high oxygen concentration, these porphyrin rings can take on an oxygen molecule onto the iron, and in regions of low oxygen concentration, then the iron can release the oxygen, and this provides a great molecule for taking up oxygen in the lungs and delivering it to the tissues. Then we'll talk a little bit about the fate of erythrocytes in the spleen and the role of the macrophages, because one of the things that happens here, because we have no protein synthesis machinery within these erythrocytes, is they basically wear out. They can't replace their own proteins. So over a period of 3 to 4 months, these cells will basically wear out. And they're cells called macrophages, and we've run into these cells before, and we're going to run into them again in the immune system. These macrophages now are recognizing the oxidized sugars on the transmembrane proteins in the erythrocytes. And when they see those oxidized sugars, they say that's a signal that those erythrocytes have been out and about for too long. It's time to destroy them. And basically, they endocytose those erythrocytes, chop them up in their lysosomes into their original parts, and maintain the iron. They'll actually pop the iron out of the porphyrin ring. That iron then will be sent off to the liver and stored in the liver. And the porphyrin rings then will go off as a waste product. We don't recycle those porphyrin rings, and we'll come around to that a little bit later. Talk about lymphatics if there's time. But where we were yesterday was to talk about the idea of beginning with an hematopoietic stem cell, and in theory, this hematopoietic stem cell could become any cell type in the red bone marrow. It could become a megakaryocyte. It could become a macrophage. It could become a T or a B lymphocyte. So it could become any one of those. But depending upon the molecular signals that it received, depending upon the growth factors and the various molecular signals, it would be determined to go into any number of these cell types. And the cell type that we talked about was the one called a proerythrocyte. And among the genetic switches that are turned on when this cell becomes a proerythrocyte is for this cell to go through a number of stages in between, but this cell becomes a normoblast. It ejects the nucleus. And it also upregulates, basically turns on genes for hemoglobin production. By the time we get to a proper erythrocyte, something like 96% of the dry weight of that erythrocyte is hemoglobin. So almost all the protein in these final cells is going to be hemoglobin, and in the process of going through this sequence of events to become a normoblast to a reticulocyte to an erythrocyte. This whole process is dedicated to largely forming this highly specialized structure that no longer has a nucleus, no longer has an endoplasmic reticulum, no longer has Golgi apparatus, has gotten rid of all of that because it takes up too much room. And so all of that space, that volume, has now been replaced such that this cell is a bag of hemoglobin. Now, if we look carefully at these erythrocytes, in fact, even if we look at these reticulocytes, they are taking on this peculiar kind of disc shape. What characterizes the reticulocyte are remnants here of ER and ribosomes. And we said yesterday that there was a kind of interface here where everything to the left of that interface was in the red bone marrow and everything to the right was out in the blood vascular system. So another way of saying that is that the reticulocyte is the last cell type that is contained within the red bone marrow and leaves the red bone marrow to go out into the blood vascular compartment. Within a day or two, these remnants of ER and ribosomes are lost, and we get an erythrocyte, which contains now almost nothing more than a bag of hemoglobin. Now, I should say, and we'll come to this a little later, that in the process of making these proteins, making these cells, that there will be transmembrane proteins. So that there will be these glycoproteins on the erythrocyte. Surface. But considering the tens of millions of these erythrocytes that we're making all of the time, one of the things we have to consider is first the shape. The shape of the erythrocyte and the hormonal system that governs its production. So, first let me put up here sort of a crude drawing of one of these erythrocytes. Typically, the diameter here of erythrocyte is in the neighborhood of 7 to 8 micrometers. The thickness of the erythrocyte is no more than 2 to 3 micrometers. And this is at its ends where it's thicker, and in the middle it's even thinner. If you look at this end on, it looks a little bit like a donut, where the middle region is thinner. And fundamentally, what we're doing here is we have this very, very thin cell, and the function of that thinness is to allow for rapid diffusion of oxygen, so that oxygen can rapidly diffuse into these cells, and so that, to a lesser extent, carbon dioxide can diffuse out. So one of the things we're going to run into here in a couple of weeks is that in the respiratory system, this is the major player. The erythrocyte is the cell type that's taking on oxygen in the lungs and giving up carbon dioxide in the lungs. So it's the major player in gas exchange. The ability of these cells, because they have something like 96% of their dry weight being composed of hemoglobin, that allows these cells, that gives these cells the ability to carry oxygen. We'll find as we get into the story on the respiration that the amount of oxygen we can carry in our blood because of these cells is something like 70 to 80 times greater than if we were simply to try to dissolve the oxygen into the plasma. So these cells are absolutely essential for carrying oxygen. And they have been modified in several ways. First, they've been modified because of their thinness, allowing for easy diffusion into these very small volumes. But secondly, we also find that they are basically a bag of the oxygen O2 carrying protein, hemoglobin. So that's basically who these guys are. But the other idea I want to bring up here is the concept of the hormonal control. And this begins with a topic we're going to spend some more time on a little later too, and that there is the structure In most of us, there are two of them. Where these things I'm drawing are meant to be the kidneys. The blood supply into the kidneys is carried directly off of the descending aorta. And the blood flows then into these structures known as the renal arteries. Now, this simple drawing doesn't tell the whole story. It turns out that something in the neighborhood of 20 to 25% of the blood leaving the left ventricle is destined for the kidneys. And that's just a technical way of saying that these kidneys are receiving an enormous blood supply. So all of the time they're receiving oxygenated blood coming from the left ventricle, flowing through the capillary beds of the kidney. Among the capillary beds of the kidney, particularly among the cells sitting right outside the capillaries, are modified fibroblasts. And these fibroblasts monitor oxygen levels in blood. And when oxygen levels begin to drop, so that we can say that a reduction in blood O2 levels in the kidney signal these very fibroblasts to release a glycoprotein hormone. This glycoprotein hormone has a name, of course. It's called erythropoietin. You'll often see this molecule, this protein, erythropoietin, abbreviated EPO. What this molecule does is it leaves the kidney and finds its way back into the red bone marrow. And in the red bone marrow, among the proerythrocytes particularly, maybe even some of the precursor cells, there are erythropoietin receptors. And these erythropoietin receptors, when they bind the EPO, enhance the survival of these cells. So basically, it's a growth factor. And these growth factors are increasing the number of proerythrocytes that survive. So now we have a greater number of proerythrocytes following down the line to the normoblast, to the reticulocytes, and then to the generation of new erythrocytes. So this is a control mechanism now to govern the number of erythrocytes that we have in our blood vascular system. And this is something we've all more or less had experience with. This is something I'm sure we've all done this to some of our poor relatives and friends who come out here from someplace along the coast, and we immediately take them up to another 2,000 feet and march them around to the mountains, asking them to climb, and they're out of breath all the time. And part of the reason for that is that they simply don't have enough erythrocytes to compensate for the lower oxygen levels that we have at this altitude. And so, but you know that if they stay here for a couple of weeks, you can repeat that experiment all over again, take them back up to the mountains, march them around, and they've pretty well recovered. And part of that recovery process is, in fact, when they first got here, the oxygen levels arriving in the kidney, in the blood in the kidney, were a little bit lower than normal. That was a signal then to tell these fibroblasts, fibrocytes, to release the erythropoietin. The erythropoietin then went back to the red bone marrow and increased the number of erythrocytes produced. The EPO has an interesting history because the EPO was recognized, probably close to 50 years ago now, that it was an important character, so an important player in generating the production of these erythrocytes. Yes?
I'm sorry, so you said that once these erythrocytes have been generated, they last 3 months?
So once these erythrocytes are generated, all the way out here, once they enter the blood vascular system, then they're only going to live for about 3 months, and they have to be replaced. And that's they're doing that they're taking on oxygen that whole 3 months and delivering oxygen, but then they have a finite lifespan. And because there are so many of these, this then indicates that every minute of your life you're generating several million of these from these proerythrocytes, so that you have adequate numbers of erythrocytes. And then again, that's under this control of the hormone erythropoietin. And as a side effect of that, one of the things you can see is that individuals in kidney disease, if their kidneys aren't working properly, one of the things that happens in kidney disease is they no longer produce erythropoietin. And we've been able to treat kidney disease for almost 50 years now by putting people onto dialysis machinery. And we could then replace many of the functions of the kidney in terms of clearing urea and osmotic and ion balances. We've been able to mimic those effects on dialysis machines for a long time. But soon after they began to keep people alive on dialysis machines, they recognized that these individuals were commonly very anemic. And they were anemic because one of the sequelae of kidney disease was these fibroblasts were no longer functioning, and so they were no longer generating erythropoietin. So the individuals were really in a bad way because they simply were tired all the time. They couldn't produce enough erythrocytes. So the pharmaceutical companies recognized that perhaps they could solve this problem if they could simply find the gene that was producing erythropoietin and then splice that gene into another animal, another cell type, and then generate from that spliced in gene into an animal model, they could generate erythropoietin. And so they did that. They basically took out the erythropoietin gene and spliced it back into, of all things, a Chinese hamster ovary cell. And the advantage of the Chinese hamster ovary cell is you could grow these up in vats, basically. So you could grow them up in enormous quantities, and each of these cells would be a little factory generating this glycoprotein, erythropoietin. Then they could harvest those cells and harvest the fluid, because it was secreting the erythropoietin into the bath. They could harvest that bath, and then from that purify erythropoietin and largely make these people on kidney dialysis have much better lives. And it was later found that in many cases the erythropoietin could be used to improve the lives of people in chemotherapy, because part of chemotherapy is to slow cell division. And among the cells dividing that get harmed are the cells giving rise to the erythrocytes. And so they could basically gin up the system for making more erythrocytes by giving people in chemotherapy erythropoietin. It seems to have helped their anemia. So again, this has been a really big boon to a number of people and has allowed many aspects of modern healthcare. And yet, there's an odd side effect to this. It didn't take long before people who were long-distance athletes, bicyclists, marathon runners, people who would get on a bicycle, for example, and get on that bicycle and bicycle at 30 miles an hour for several hours. That's a tremendous aerobic feat. And the money involved in winning those races was pretty big. And so there was a strong driving force for people to start being able to stay on the bicycle and bicycle faster for those periods of time. And so they realized, well, maybe if they took some erythropoietin, they could increase their hematocrit, have better oxygen carrying capacity, and compete better. And it seemed to have worked for quite some time. And what's more is they said, we'll never get caught because the erythropoietin is the same gene as the human erythropoietin gene. It was just spliced into another animal. But one of the things that happened as they began to develop these erythropoietins is they started to select for a change in the glycosylation pattern on the outside of those cells. And so by changing they changed the glycosylation pattern on the erythropoietin molecule. And by changing the glycosylation pattern, what they were trying to do is make it stay in the system longer. Typically, it only has a half-life of a couple of days, and so they could increase the half-life. So by changing the glycosylation pattern, they now shifted the characteristics of the erythropoietin. And they could now recognize in tests the new kind of erythropoietin. And they could look at the ratios of the new erythropoietins that were generated from the Chinese hamster ovary cells from the particular athlete. And because they had frozen back the aliquots of blood after each of the races, the top finishers had to give a blood aliquot, and they froze those back. They went back like 10 years, 15 years, and checked the erythropoietin characteristics in the blood. And that's how Lance Armstrong got caught, because they went back and checked, and sure enough, almost all of these athletes were using erythropoietin. And they got caught because they didn't understand the changes in the molecular changes in the erythropoietin that had taken place pharmaceutically to improve the quality of the drug. And they should have been better pharmacologists and they wouldn't have gotten caught. But we have decided that this is illegal, but still people do something called blood packing, the same thing. What blood packing is you take an aliquot of your own blood, freeze it back sometime before a race, so several weeks before a race. Then you go ahead and increase your hematocrit back to normal, and just the night before the race, you take on an extra pint or so of blood. And that increases the hematocrit. It's very hard to catch that. And it apparently helps a lot. This was started in the mid-60s. There was a Finnish marathonist. I never remember his name, and he won, I think it was the 64, 68 Olympic marathon, and he had figured out that if he would blood pack before a race, he could run much faster times, and that was the initiation of this whole thing. And that too now is illegal, but it's very difficult to catch. Yes?
So for when it basically do its job increasing your hemoglobin, how many takes about
So how long, the question is, how long does it really take to increase the number of erythrocytes? I think you can actually see an increase in the number of erythrocytes within a week to 10 days. I'm not sure when you reach the maximum effects of erythropoietin, but this whole process, increasing erythropoietin from the kidneys will upregulate the hematopoietic stem cells to give rise through this series of events to increase the number of erythrocytes. I think it's within 10 days, so a week to 10 days. Yes?
Are there a lot of negative effects to the rest of your organs and stuff when you change these up and down a lot?
Are there negative effects to the erythropoietin? Well, probably not, if you're careful. But one of the things they found in the early days of erythropoietin is that there were these exquisitely well-trained athletes at the peak of their athletic lives in their mid-20s, and suddenly in the middle of a race they'd die of a heart attack or a stroke. And it turned out that by increasing the hematocrit levels and increasing the iron levels in the blood, that they now biased themselves toward a higher probability of heart attack and stroke. So they'd throw a clot, throw an embolism, and then have a heart attack or stroke. So that is a bad side effect. But for most people who are cancer patients or on kidney dialysis, taking some EPO is probably not such a bad thing. Right? Anything else? Well, not. Then let's look a little bit at the erythrocyte itself. Let me show you a picture so I get a get a better image of this. And then we'll drill down. So what this is simply the series of events that we talked about last time. And if you go to a number of textbooks, you'll find that depending on where you look, that there will be a number of intervening cells in this. And if you look in some places, you'll see where most of the hemoglobin is being produced. It's between the proerythrocyte and the normoblast. But this is what I really wanted to show you, is this image of an erythrocyte. So when I draw it in cross-section on the board, it looks a little like a dumbbell, but in fact, it's a disc. And it's said to be a biconcave disc because it's thinner in the middle. The diameter of the disc is about 7 to 8 micrometers, and the thickness at the edges is no more than about 2 micrometers, and even thinner in the middle part. Because, again, the thin cells, the short diffusion distances, allow for oxygen to easily diffuse across the phospholipid bilayer and bind to hemoglobin molecules in that biconcave disc. So let's take a minute, and I'll draw it on the board, and then we'll come back to some pretty pictures. To provide a kind of description here, let's leave this. Let's take a moment and discuss a little bit about the major molecule in the erythrocyte, and that, of course, is hemoglobin. The overwhelming molecule in an erythrocyte is this protein called hemoglobin. And in fact, you can really look at these erythrocytes and think of them simply as a bag of hemoglobin molecules, and the bag basically has gotten rid of all of its other cellular characteristics, paying a pretty heavy price, so that the cell itself now is simply chock full of hemoglobin molecules. So let's take this panel and use it to describe the structure of hemoglobin. Now, in each one of these cells, there's going to be something in the neighborhood of about 250 million copies of hemoglobin. Each hemoglobin molecule is constructed of 4 proteins. Of the 4 proteins, there are 2 alpha subunits, well, I should say alpha chains, and 2 beta chains. This is in the adult. We have 2 alphas and 2 betas in the adult. When we talk about respiration a little later, we'll mention the idea that in the fetus there are 2 alpha chains and 2 gamma chains. And it turns out that the 2 alphas and 2 gammas have a slightly higher affinity for oxygen than the 2 alphas and 2 betas. And if you think about that for a minute, if you're living in utero and getting all of your oxygen from your mother, it's probably a good idea to have a higher affinity to your hemoglobin than your mother's, so you can basically take it from mom. But in the adult, we have 2 alphas and 2 betas. Each protein chain contains an iron atom in a porphyrin. In a porphyrin ring. So taken together, since the 2 alphas and the 2 betas each contain a porphyrin ring with an iron atom, this means taken together, these molecules contain 4 iron atoms. The iron atom is where oxygen binds. So taking those numbers and recognizing there are 250 million hemoglobin molecules in each erythrocyte, and each hemoglobin molecule binds 4 oxygen atoms, we can now bind 10 to the 9th oxygen molecules in one erythrocyte. These are remarkable oxygen-carrying containers, and they're able to carry so much oxygen because of the characteristics of these alpha and beta chains and their corresponding iron in the porphyrin ring. Yes?
What causes the gamma chain? Like, why not just keep something that has a higher?
So the question here is, since I brought up the question of the gamma chain, why don't we just keep them? And the answer to that is, it's great if you're trying to get oxygen from your mother in utero, but it's not so great when you're trying to give up the oxygen to your tissues. So if it has a higher affinity, then it doesn't have quite as great an ability to give up that oxygen when it gets out into the tissues. And that's one of the beauties of this molecule, and we'll come back to this in a moment. One of the great beauties of this molecule is that in regions of high oxygen, it can basically saturate. We can effectively occupy all of these iron, all billion of these iron atoms can be occupied by oxygen. But it's not such a tight binding that when this hemoglobin and the erythrocytes get out into the tissues, which are requiring oxygen to be the final electron acceptor to make ATP, once we get out into the tissues, we want those hemoglobin molecules to give up the oxygen. And so the gamma hemoglobins are not very good at that, and so that's why you replace them. Put your phone away, I'd appreciate it. Yes?
At what point do they change over? Is it like as soon as you're born, like the first month?
So the question is, when do they change over? They change over just about the time of birth. And in some cases, we're getting a little ahead of ourselves here, but in some cases, you may know of newborns who were jaundiced. And they're jaundiced because right after the switch from the one kind of hemoglobin to the other, they have to get rid of all that hemoglobin. And when they get rid of all that hemoglobin, they end up with these porphyrin rings. And the porphyrin rings then take on a kind of yellow color. And as long as the liver's working fine and they can move the porphyrin rings out into the gut and get rid of it, it's not a problem. But if something goes wrong, then they begin to build up these porphyrin rings under the skin and they turn yellow. And that's the jaundice. But it's easily fixed. A little bit of ultraviolet light, and it breaks up those porphyrin rings. But let's hold on. I'll come back to that when we talk about porphyrin rings. Anything else? So when we look at this molecule, and it's going to be, I'm going to do this pretty crudely. That we have these protein molecules that obey all the rules we've talked about so far with proteins. That is, they have an amino terminus, they have a carboxy terminus. And so if I sort of draw these as squiggles, they're quite large proteins, and they're folded into a three-dimensional shape. And each of the proteins the alpha chains and the 2 beta chains, I'll put in here in green, contain within them the structure I'm going to put in as a circle. This is meant to be the porphyrin ring. Now, I don't want to get too deep into the weeds on the porphyrin ring, and if you take a biochemistry course, you'll spend a lot of time looking at this because the resonance structure of the ring is pretty interesting. But all I want you to see is that in the middle of this porphyrin ring is an iron. And then covalently linked to that porphyrin ring at 4 sites will be nitrogens in a 5-membered ring. In fact, chemists among you, it's an imidazole ring. And then these rings are also connected by ring structures, and I don't want to get too much into that. But the idea here is that by having this iron covalently linked to these nitrogens in the porphyrin ring, there's a kind of electron sharing here in such a way that this iron ends up with having a charge of +2. Because of the electron sharing and that +2 charge, that now allows for an oxygen to come down onto this iron and bind to the iron. It'll actually pick up an extra electron and be a superoxide, but that's a detail. The main idea here is that the oxygen can bind to the iron in this ring, change it from the +2 to a +3 state by borrowing an electron, and now it's bound to the iron, but it's not bound very tightly. And this comes back to the question that came up earlier. In the lung, where we have high concentrations of oxygen in the airspace, we can now allow oxygen to come onto those iron atoms in the porphyrin ring and the hemoglobin. So in the lung, the equation is biased toward binding oxygen to iron. But this equation is now in the reverse, where iron relinquishes oxygen in low oxygen environments. Now remember that out in the tissues, in the muscle, in the gut, in the brain, what we're doing is we're using oxygen as the final electron acceptor in all of our in all of the mitochondria in our cells. And when we do that, we generate water. So we deliver oxygen to the tissues, we convert that oxygen into water through the process of the electron transport chain and generating ATP. So we're using up oxygen. Then what we have to do then is we have to take the carbon dioxide that's generated there back to the lung, but the oxygen is going to be in lower concentration in the tissues because it's being used by the mitochondria and converted into carbon dioxide and water. And so when that happens, then we have lower concentrations of oxygen out in the tissues. And this molecule, which we'll talk about here, simply with its iron, then will now relinquish or take on oxygen. Take a biochemistry course, you'll find there are other exquisite control mechanisms in here which are going to regulate whether these porphyrin rings have a high affinity for oxygen or a lower affinity. And we can change that over a broad range. So the long and the short of this is we've generated these erythrocytes. They're not real cells, and they have a finite lifespan. And so, but their function is to be really important. Their function is to play a really important role in delivering oxygen to the tissues. And we need to have these hemoglobin molecules in this organization to do that. So let me show you a picture of the porphyrin ring. And then we'll talk about the fate of these cells. So So this shows in more detail the structure of the hemoglobin. So here's the iron in the middle, coordinated, it's in fact covalently bonded to these nitrogens, and then this great ring structure. And the great ring structure now, because of its resonance, is borrowing electrons from the iron and putting it in the appropriate state so that oxygen can bind to it. And we're carrying the oxygen on these iron molecules. And up here, it's just a crude drawing trying to show that these porphyrin rings are embedded within the protein. And within the protein, then, you have these sites where we can bind the oxygen. So in the last few minutes here, though, let me describe what happens to these erythrocytes. We started out with a discussion of where they came from, and we emphasized that they have a finite lifespan because they've lost their protein synthesis machinery. But now what we want to think about is what becomes of them. And so I want to take this panel and describe the fate. This is erythrocyte fate. Basically, for most of us who have our spleens, the fate of the erythrocyte is the end of the erythrocyte is met in the spleen. And others who have had splenectomies, it's in the liver. But what's happening is that erythrocytes with oxidized sugars on glycoproteins are recognized by macrophages, mostly in the spleen. I want to take a moment here to describe the spleen because this is going to become important in the next couple of days, where the spleen is the structure with a tremendous blood supply. It has a blood supply through a splenic artery, and it's drained by a splenic vein. But of course, in between the two will be capillaries. But these capillaries are unusual because they contain large gaps between adjacent endothelial cells. These gaps are so big that erythrocytes can escape and reside for periods of time in the spleen called the red pulp. And if we look at the red pulp, we find the red pulp is enriched in macrophages. Put this in the backboard. Where there are macrophages, these large cells, which can recognize on the erythrocyte the transmembrane proteins with their oxidized sugars. These macrophages can recognize these molecules and then, through a process of endocytosis, draw the erythrocyte into a vesicle and ship the erythrocyte toward an old friend out here called the lysosome. And in the lysosome, we'll basically destroy the erythrocyte and scavenge the iron and dispose of the porphyrin ring. So it's the macrophages in the red pulp of the spleen which are involved in getting rid of these worn out erythrocytes. But that's not really a problem because we're continuously making new ones. With that, I'll let you go.